Question: what is a chemical bond, and why is it important in forming molecules? Answer: a chemical bond is an attractive force between atoms that holds them together in a molecule. It forms when atoms share or transfer electrons to achieve stable electron configurations. Covalent bonds involve electron sharing, like in water, while ionic bonds involve electron transfer, as in sodium chloride. Chemical bonds determine a molecule's structure, properties, and reactivity. For example, strong bonds in diamond make it hard, while weaker bonds in graphite allow layering. Bonds are crucial for forming stable compounds, enabling diverse substances in nature and industry, from DNA to pharmaceuticals. Question: explain the concept of electronegativity and its role in bond polarity. Answer: electronegativity measures an atom's ability to attract electrons in a chemical bond. Elements like oxygen and fluorine have high electronegativity, pulling electrons closer. In a bond, a large electronegativity difference, like in HCl, creates a polar bond with partial positive and negative charges. This polarity affects properties like solubility and boiling point. For instance, water's polarity, due to oxygen's high electronegativity, enables it to dissolve salts. Electronegativity trends increase across a period and decrease down a group in the periodic table, influencing molecular behavior in reactions and interactions. Question: what is the pH scale, and how does it relate to acidity? Answer: the pH scale measures a solution's acidity or basicity, ranging from 0 to 14. A pH of 7 is neutral, below 7 is acidic, and above 7 is basic. It's based on the concentration of hydrogen ions, H+. Lower pH means higher H+ concentration. For example, lemon juice, pH 2, is acidic due to high H+, while ammonia, pH 11, is basic with low H+. The scale is logarithmic, so a pH change of 1 represents a 10-fold change in H+ concentration, critical for chemical reactions and biological processes. Question: describe the role of a buffer in maintaining pH. Answer: a buffer is a solution that resists pH changes when acids or bases are added. It typically contains a weak acid and its conjugate base, like acetic acid and acetate in vinegar. When H+ ions are added, the conjugate base neutralizes them. When OH ions are added, the weak acid reacts. This maintains a stable pH, crucial in biological systems like blood, where a bicarbonate buffer keeps pH near 7.4. Buffers are also used in chemical experiments to ensure consistent conditions, preventing unwanted reactions caused by pH fluctuations. Question: what is Le Chatelier's principle, and how does it apply to chemical equilibrium? Answer: Le Chatelier's principle states that a system at equilibrium adjusts to counteract changes in conditions like concentration, temperature, or pressure. For example, in the reaction N2 plus 3H2, or 2NH3, increasing N2 concentration shifts the equilibrium toward producing more NH3. Higher pressure favors the side with fewer gas molecules, NH3, and increasing temperature shifts it toward the endothermic direction. This principle helps predict how reactions respond to changes, guiding industrial processes like ammonia synthesis in the Haber process to optimize yield by adjusting conditions strategically. Question: explain why carbon dioxide is a greenhouse gas. Answer: carbon dioxide, CO2, is a greenhouse gas because it absorbs and traps infrared radiation in the atmosphere. Its molecular structure allows it to vibrate when it absorbs heat energy, preventing it from escaping into space. This contributes to the greenhouse effect, warming the Earth. CO2 is released from burning fossil fuels, deforestation, and industrial processes. Unlike water vapor, CO2 persists longer in the atmosphere, amplifying global warming. Its concentration has risen significantly, intensifying climate change. Reducing CO2 emissions is critical for mitigating environmental impacts, as seen in international climate agreements. Question: what is an exothermic reaction, and give an example? Answer: an exothermic reaction releases heat to its surroundings, resulting in a negative enthalpy change, dH0. It occurs when the energy of products is lower than reactants, liberating energy, often as heat. A common example is combustion, like burning methane, CH4 plus 2O2, CO2 plus 2H2O. This reaction produces heat used in gas stoves or power plants. Exothermic reactions are vital in energy production and metabolic processes, like cellular respiration, where glucose breakdown releases energy for bodily functions. The heat release makes them feel warm to the touch. Question: describe the structure of an atom and its key components. Answer: an atom consists of a nucleus surrounded by an electron cloud. The nucleus contains protons, positively charged, and neutrons, neutral, determining the atom's mass. Electrons, negatively charged, orbit the nucleus in energy levels. For example, a carbon atom has 6 protons, 6 neutrons, and 6 electrons. Protons and neutrons contribute to the atomic mass, while the number of protons, atomic number, defines the element. Electrons participate in chemical bonding. The atom's small size and balanced charges make it neutral, forming the building blocks of all matter. Question: what is the difference between an element and a compound? Answer: an element is a pure substance made of one type of atom, defined by its atomic number, like oxygen, O, or iron, Fe. A compound is a substance formed when 2 or more elements chemically bond in a fixed ratio, like water, H2O, or carbon dioxide, CO2. Elements cannot be broken down chemically, while compounds can be separated into their constituent elements through reactions. For example, electrolysis splits water into hydrogen and oxygen. Elements are listed on the periodic table, while compounds have unique properties distinct from their elements. Question: explain the concept of molar mass and its use in calculations. Answer: molar mass is the mass of 1 mole of a substance, expressed in grams per mole, g-mol. It's calculated by summing the atomic masses of a molecule's atoms. For example, water, H2O, has a molar mass of 18 gmol, 2x1 for H plus 16 for O. Molar mass is used in stoichiometry to convert between grams and moles, enabling calculations of reactants or products in chemical reactions. For instance, to find how much CO2 is produced from burning 16 G of methane, molar mass helps determine mole ratios and yields. Question: what is Avogadro's number and why is it important? Answer: Avogadro's number, 6.022 x 10^23, represents the number of particles, atoms, molecules in 1 mole of a substance. It's a fundamental constant in chemistry, linking microscopic and macroscopic scales. For example, 1 mole of water, 18 G, contains 6.0222 x 10^23 H2O molecules. It's used in calculations to convert between moles, particles, and mass, essential for stoichiometry in reactions. For instance, knowing Avogadro's number helps calculate how many molecules react in a process, like in gas laws or determining reaction yields in industrial chemistry. Question: describe the role of catalysts in industrial processes. Answer: catalysts accelerate chemical reactions in industrial processes without being consumed, lowering activation energy. For example, in the Haber process, iron catalyzes ammonia, NH3, production from nitrogen and hydrogen, increasing efficiency. In petroleum refining, catalysts like platinum facilitate cracking of hydrocarbons into fuels. Catalysts reduce energy costs, enhance reaction rates, and improve yields, making processes economically viable. They're reusable and specific, designed for particular reactions. Their use in industries like pharmaceuticals and fertilizers is crucial for producing essential compounds at scale while minimizing environmental impact through efficient reactions. Question: what is the ideal gas law and how is it applied? Answer: the ideal gas law, PV/NRT, relates pressure, P, volume, V, moles, N, gas constant, R, and temperature, T, for an ideal gas. It predicts gas behavior under varying conditions. For example, to find the volume of 2 moles of gas at 1 atm and 273 K, use V if NRTP with R if 0.0821 L atm mol K. Plugging in values gives V if 2x 0.0821 x 273 144.8 L. It's used in chemistry to calculate gas properties in reactions, like in combustion or industrial gas storage. Question: explain the concept of oxidation and reduction in redox reactions. Answer: in redox reactions, oxidation involves electron loss, while reduction involves electron gain. For example, in the EA, reaction Zn plus Cu2 plus, Zn2 plus Cu, zinc is oxidized, loses electrons forming Zn2 plus, and copper ions are reduced, gain electrons forming Q. The processes occur simultaneously, with electrons transferring from the oxidized to the reduced species. Redox reactions are vital in batteries, where electron flow generates electricity, and in metabolism, like cellular respiration. The substance oxidized is the reducing agent, and the substance reduced is the oxidizing agent, driving chemical transformations. Question: what is a mole, and how is it used in chemistry? Answer: a mole is a unit measuring the amount of substance equal to 6mo22 x 1023 particles, Avogadro's number. It connects mass to the number of atoms or molecules. For example, 1 mole of carbon, 12 G, contains 6.022 x 1023 carbon atoms. In chemistry, moles are used in stoichiometry to calculate reactant or product quantities in reactions. For instance, in 2H2 plus O2, 2H2O, 2 moles of H2 react with 1 mole of O2 to produce 2 moles of water, guiding precise measurements in experiments and industrial processes.